Hey everybody, these are the solutions for the quiz posted on June 15th. So let's get through them. So number one, we have a golf ball that is hit off a tee with some instrument, and it has an initial velocity of 40 meters per second. And then it also reaches a maximum height in its trajectory of 55 meters. We want to find how fast is it going at y max. Now, a couple of you asked me if it's going to be 0 at y max, and I can tell you that, remember how projectile motion works, Vy will be 0, that is, velocity in the vertical direction is going to be 0 at its maximum height, but its forward velocity is going to be non-zero. So we could actually do this two ways. We can solve this either as a projectile problem, or we could solve this using conservation of energy. So let's do conservation of energy. I think it's a little simpler. So conservation of energy tells us that EI equals EF. That is, its total mechanical energy right after it's hit off the tee is equal to its total mechanical energy when it's at its maximum height. So let's write down what those energies are. When it's at the tee, it's presumably on the ground, where we'll take y to be 0, so it has no gravitational potential energy. So all of its initial energy is going to be kinetic energy. Then its final energy is going to be some kinetic energy from its forward motion, so we'll call that Kf, and then some gravitational potential energy from being above ground level. So let's substitute in the appropriate equations for those. So we get 1/2 mvi squared equals 1/2 mvf squared plus mg y max, which is the gravitational potential energy it has at the apex of its trajectory. All right, so we want to find Vf. So we can solve this equation for Vf by moving over gravitational potential energy, getting rid of the factor of mass, getting rid of common factors, and it turns out that we can write down final velocity to be the square root of Vi squared minus 2Gy. So, substituting in, our initial velocity is 40 meters per second. Then we have minus 2 times g, which as always is 9.81 meters per second squared. And we have y max, which is 55 meters. And all that goes under a square root sign. So, when I plug that into my calculator, I find that the velocity of the golf ball at the apex of its trajectory is going to be 22.8 meters per second. Nope, let me move the page up so you can see that. 22.8 meters per second. All right, number 2. So we have a 100-gram ball forced into a horizontal tube with a spring at the end. So here's our horizontal tube. Forgive my artistic skills, they're terrible. Here's the spring at the end. And we force a ball into it. And the spring is compressed 10 centimeters from its equilibrium condition. And the spring has a spring constant of 600 newtons per meter. And we want to find how fast the ball is going when the spring returns to its equilibrium position after releasing it. Okay, so this again is just conservation of energy. But in this case, the only source of potential energy is spring potential energy because we're not changing height. As long as height remains constant, there's no gravitational potential energy effects. So in this case, conservation of energy of energy can be written as always, EI equals EF. And here, the initial energy is just the spring potential energy that it gets from being compressed. So that's 1/2 kx squared. And then when the spring is at equilibrium, it's no longer compressed or stretched, so it has no spring potential energy. So once it's at equilibrium, all of the energy in the system is just in the ball's kinetic energy. And we'll call that 1/2 mvf squared. And so what we really need to do is solve for, again, vf squared. So doing that gives vf equals, let's see, square root. We can drop that factor of 1/2. Kx, square root of kx squared over m. And then substituting, we get k, which is 600 newtons per meter. We have x, which is 10 centimeters, or 0.100 meters. Remember to convert to MKS units. And then we have the mass of the ball, which is 100 grams, or 0.1 kilograms. And then plugging all that in, we find that the velocity of the ball is 7.75 meters per second. So that's number 2. All right, number 3. Similar problem, but there's a wrinkle. So if everything else is the same, that is, we compress the spring the same amount, we have the same weight ball, we have the same spring with the same spring constant, but instead the tube is vertical, we want to find out how fast the ball is going when the spring returns to equilibrium. So we take the equilibrium point, we'll take it as y equals 0 this time, but the same principle will hold true for writing down our conservation of energy equation. Then there's actually going to be 2 sources of energy. There's going to be spring potential energy, and there's going to be gravitational potential energy. So let's write down conservation of energy. We have 1/2 ky squared plus mgyi. And then the final energy is also going to have 2 terms. It's going to have the kinetic energy, 1/2 mvf squared, but it's also going to have a gravitational potential energy. So we want to find out how fast the ball is going when the spring returns to equilibrium. Let's think about this a bit. So yi is going to be minus 10 centimeters, since we're compressing the spring from its equilibrium point. Yf, however, is actually going to be 0, because we're defining the equilibrium point of the spring as 0. So let's see. That means that our gravitational potential energy term here is going to cancel. Then we can solve for Vf. So let's see. Square root k over m yi squared plus two gyi. All that goes under the square root sign, and that's our expression for final velocity. So if we substitute, k is 600 newtons per meter. We have a mass of 100 grams. And we have an initial y position of minus 10 centimeters, so minus 0.100 meters. And we have 2 times 9.81 meters per second squared, again, times minus 0.100 meters. All of that goes under the square root sign. So let me work that through in my calculator. All right, and I find the velocity to be 7.62 meters per second. Notice that because of the gravitational potential energy, oops, let me move that up so you can see it. Because of the gravitational potential energy, the spring's actually going a little slower, or the ball's going a little slower when the spring returns to equilibrium compared to the horizontal version of this problem, and that's due to the extra potential energy it has to overcome to make it to equilibrium. Okay, number 4. So, number 4, we have a car moving at constant speed of 15 meters per second. And it's being driven by an engine that delivers 40 HP of power. So the first thing we should do is convert that 40 HP to MKS units. So let's see, 40 horsepower. And we know there's 746 watts in 1 horsepower. So 40 horsepower is equal to about 29,800 watts, or 29.8 kilowatts. And we want to find the friction force. So how do we do that? The key thing to realize is that the car is moving at a constant speed. And what that means is that the net force is 0. So if we write down our net force, we should get this. We have the force being put out by the engine, and we have the friction force, 0. Excuse me. So the force being put out by friction is just the negative of the engine force. Well, what's the engine force? The engine force we can get using one of our definitions for power. Remember, power can be expressed as force applied as a velocity, or to a velocity. Force times velocity. So that means that the friction force is just going to be the power of the engine over the velocity that it's driving the car at. So let's see, our power is 29,800 watts. The car is traveling at 15 meters per second. And so the force of friction should be negative 1990 newtons. Oops, sorry, I keep forgetting to move the paper up. There you can see that now. All right, so that's it for this quiz.